name is Emmanuel, and I'm going to talk about MDP.jl, the Julia library of molecular dynamics potentials. In this project, we aim to develop an open source code for active training, fast calculation, and uncertainty quantification of molecular dynamics potentials for atomistic simulations of materials. The building blocks of our code include automatic code generation, multi-level parallel force calculation, automatic differentiation, advanced compiler technologies, and Bayesian inference. Molecular dynamic simulations require a potential energy function to describe the force field governing the interaction among atoms. Current MD potentials present limitations when solving complex study cases as ultra-high temperature ceramics in hypersonic flows. Particularly, existing React FF and COM potentials do not produce satisfactory results since they require retraining, while machine learning potentials demand a significant amount of DFT data for the training process. Currently, there are no open source libraries that allow for training coupled machine learning and empirical potentials, and at the same time offer other key features such as quantifying uncertainties in the training machine learning potentials or identifying near-optimal configurations to include in the training data. We develop a new software to fill this gap, aiming to provide fast and accurate potentials for classical MD simulations on exascale supercomputers. MDP consists of new machine learning potentials and automatically generates C++ implementations of many-body empirical potentials directly from their mathematical expressions. MDP implements multi-level parallel force calculation algorithms that are well suited to shared memory processors for both machine learning and many-body empirical potentials. It speeds up force calculation on a Titan V GPU card by a factor of 1000 faster than on a single-core CPU of Intel Xeon E5 2050 CPU. MDP leverages Enzyme to automatically calculate gradients by performing reverse-mode automatic differentiation of statistically analyzable LLVM intermediate representation. By differentiating code after optimization, Enzyme is able to create substantially faster derivatives than existing tools that differentiate code before optimization. Enzyme allows MDP to not only optimize coupled machine learning and empirical potentials, but quantify their uncertainties through Bayesian inference and sensitive analysis. Furthermore, MDP source code is analyzed and compiled using OpenCL compilers and productivity tools to accelerate its runtime performance. In the next phase of development, we will focus on demonstrating and comparing MDP with other well-established potentials such as SNAP, GAP, and DeepMD on a number of validation cases. We will also develop an end-to-end prototype pipeline linking MDP to DFT codes such as Quantum Expresso or DFTK.jl, and the MD code Embody Simulator.jl. We are also working on integrating MDP with ACE and LAMPS to ease the effort of training potentials and running MD simulations. Thank you for your time.